Hi, my name is Jim, and today we're going to talk about a second way of solving parallel circuits, which is the current method. And before we begin, let's just remember that in a series circuit, the current is what's common. It flows through all the elements of the circuit. And in a parallel circuit, what's common is the voltage, which is across each element in the circuit. And it can be confusing sometimes if these are drawn in different ways. For example, if this 25 ohms were down here, say, drawn horizontally, you may not recognize it as being in parallel. So kind of the rule is that if top wire of one component connects to the top wire of another component, and the bottom wire of a component connects to the bottom wire of the other component, they're in fact in parallel. So these are phasors, and I'm not going to use phasor notation here. There's enough ink on the paper. So I total, according to Kirchhoff's current law, is going to be equal to the inductor current plus the current through the 25 ohm resistor plus the current through the 40 ohm resistor plus the current through the capacitor. So what we can see by looking at this is that more current is going to be flowing through the inductor than is going to be flowing through the capacitor. Therefore, the inductor per se will dominate the circuit, and when we combine these parts together, it'll have an inductor flavor. Now in a series circuit, the opposite is true. The one with the highest reactance determines whether it's going to be an inductive or a capacitive circuit. So we can tell right now from the J15 versus the negative J20 that more current is going to be flowing through L. So let's go find the currents then. The current through the inductor is 10 volts divided by 15 at plus 90 degrees ohms, and that's J15 in rectangular form converted into polar form because of the division, and that gives us 666.6 repeat at negative 90 degrees milliamperes. So what that says is the inductor current is lagging the source voltage by 90 degrees, just like it should. Next we'll find IR total, and I'm going to be using the combined resistance here. Taking these two with product over sum gives me 15.36, and then later if I want to break out and find the individual currents, which I will do, it's a very simple matter to do that. So now I'm just going to lump these two together, and it's 15.36 ohms. The sanity check on this is that when resistors are in parallel, the value has to be lower than the lowest resistor. So I'm kind of pleased with this number. And to find the resistor total, and I put angles on them just to do it, is 10 at 0 degrees volts divided by 15.36 at 0 degrees ohms, and that comes out to be 651 at 0 degrees milliamperes. Likewise, we have the capacitor current, 10 at 0 degrees volts divided by 20 at negative 90 degrees ohms. That would be negative J20 in rectangular form converted into polar form here for the division, and that comes out to be 500 at plus 90 degrees milliamperes. So through the capacitor, what we see is that the current leads the voltage of the source by 90 degrees, just as it should. Now if we want to come up with a current plot, what we would do on the real axis would be set 651 milliamperes. That would be our current flow here for the resistance, 651. And then for the capacitor, we would have plus J, 500 milliamperes. And then for the inductor, we would have negative J, 666 milliamperes. So the J's are like terms, so I can add them together. And the net result is we have a resistance value that's the same, 651 ohms, and the sum of the capacitor current and the inductor current leaves us at negative J, 166 milliamperes. So what we would need to do then would be find I total, and we'll be doing that in a minute. So I total in rectangular form is 651 at a negative J166, and to get it in the polar form so we can kind of manipulate it around a little bit, it's business as usual. We'll take the square root of the sum of the squares of the resistor current and equivalent inductive current. Now, this isn't a physical part here. This is the difference between the L we started with combined with the C we started with, giving us an L equivalent that looks like 166 milliamperes. Could we find out what that reactance value is? Very easily. Divide 20 volts by 166 milliamperes and you would have the inductive reactance of L equivalent. So our total comes up to be 672 at negative 14.3 degrees milliamperes. So you can see kind of why the angle is so small, per se, is that we have 651 mils flowing through the resistor and only 166 milliamperes flowing through the equivalent inductive circuit. So we're going to get a relatively small angle. And working that out, what we get is 488 at plus 14.3 degrees ohms. So the current plot of this, if we wanted to do the equivalent, which would be this guy here would be negative J166, that's that guy, and 651 milliamperes for the resistive component, and we would get our total current 672 would be the hypotenuse, and the angle between the hypotenuse and the real axis would be our 14.3 degrees. I didn't call it negative 14.3 because it's labeled in quadrant 4 as such, so you would know that. So if I want to do a z-plot, what I have is z in polar, and I don't plot so well in polar. I need a protractor and a ruler, so I'm going to break it down into real and imaginary, and then do a projection on it. So the z total real is 14.88 cosine of the angle, comes out to be 14.41 ohms, and z total imaginary is same thing except the sine of 14.3, and that comes out to be J 3.68 ohms. So the z-plot on this would be, here's our J 3.68 ohms, and here's our real component of 14.41 ohms. Do the dot thing, draw a line from the origin to the convergence of the dots. That'll be our 14.88 ohms for total and polar. And then sitting in the middle here we have 14.3 degrees difference between the hypotenuse and the side adjacent, which is the real axis. So what we end up with here, whether we wanted to or not, is a series equivalent circuit. So what that means is that if I take 14.41 ohms and put it in series with J 3.68 ohms, it looks exactly like this circuit. An external source could not tell the difference. And that's true at one and only one frequency. In fact, this circuit is exactly equivalent to this circuit. Now, what we have to be careful of is confusing the series resistance with the parallel resistance. So RS is not equal to RP, our parallel. And LS, the series, is not equal to LP, the parallel, except at 45 degrees. So that's the only time they're equal. And what you can kind of see, what we're doing here is we can go back and forth between series and parallel circuits. Now the last part, if I wanted to find the resistor current, IR25 would simply be equal to 10 volts divided by 25 ohms, giving 400 milliamperes, and IR40 would be 10 volts divided by 40 ohms, giving 250 milliamperes. And, as you might suspect, if we add them together, we should get 650 milliamperes, which we got before, and that checks out. So I'm happy with the calculations. So that's the current method, and thank you for watching.